So let's look at drawing the shear force and bending moment diagrams for these two structures and using our graphical technique. Now, just to speed things up a little bit, I know you guys can do this, but I'm going to go ahead and write that I know the reaction force here is P, and the reaction moment here is PL. If you don't see that, you can quickly draw the free body diagram for this structure and assume that. Now, what kind of shear force is that?
Positive.
That's positive. What kind of bending moment is that? Negative. So I know my starting points. On this free end, the shear is going to be a little tricky. I'll talk about that in a second. But what's the moment? Zero. It's unrestrained. There's no moment there. So let's draw our shear diagram. I think these are going to be in kips and kip feet. So what's my starting shear force? P. So I'll mark it there. P. Now, since we're here, let's talk about this for a little second. If I looked at just a free body diagram of that very end where my force P is, and I made a little cut right there. And I made a cut so it's just like dx from the end. All right? And I'll just draw that right here. So there's my little free body, dx. On the far right edge is the force P. And then on that left edge, I'm going to assume positive shear force. Because on the left side, positive is up, right? What's the equilibrium of this tell me that shear force is going to be? Positive P. Right? So that means the shear force at the end of the beam is going to be what? Should be positive P. So I know my beginning and end points.
Can you repeat that?
Which part?
So you cut it right at the end and then you drew...
Yes, see, I made a little cut here, and then that's the free body diagram of that cut. So there's my little beam segment. On the far right edge is P, and then there's my internal force, positive shear. See that?
Yeah.
So if you just sum forces in the y direction, you'll have shear up and P down. So when you solve for shear, you just get P, positive P. So I know the shear at the end of the beam is positive P. Now, I know that the change in shear between any 2 points is the area under the load curve. What's the area of my load curve from the left to the right? 0. So there's no change. So if I start at positive P, add nothing to it, I get positive P. That matches. And I know the slope of my shear diagram at every point is equal to the load. What's the load everywhere on this beam? 0. So I have no slope. 0 slope looks like this. And I now have a structure that has constant shear force across the whole thing. I just took the things I knew from equilibrium and these relationships between shear force and load. I was able to construct. And what about moment? So again, starting at the left side, what kind of bending moment is that? Negative. So that'd be negative PL. What kind of bending moment do I have on the free end? 0. So I better hit 0. And I know that the change in moment between any 2 points is the area under the shear diagram. What's the area under the shear diagram? What's a rectangle? Base L times height P. That's positive PL, right? So negative PL plus positive PL is 0. Hey, that works. And the change in the slope of the moment diagram is equal to the shear. And what's the value of the shear everywhere? It's P, and it's positive. So that means my curve everywhere should be positive slope, constant. In fact, it would be 1 to p. And there's my moment diagram. So where's my maximum moment? Right there at the fixed connection. And what's the value? Negative PL. What's the maximum shear? P. Where does it occur? Everywhere. So I am able to look at the graphs once connected, and I can find maximum values and where they're located pretty quickly. If you had a graph, except for really simple graphs, if you had a function, sometimes it's hard to know where the maximum value of a function is. You have to take the derivative, say it equals 0, and find that point. It could be a little tedious mathematically. But from this graphs, for these loads, we can find them fairly quickly. So let's redo this, except we're going to do it for this one with applied moment at the end. Well, there's no force on this beam, so there's no force reaction. There's an applied moment, so there's a moment reaction. Right? If I sum forces in the y direction, well, there are no forces to sum, so I don't need a reaction. So what's my shear diagram going to look like? What's the shear here? 0. What's the shear at the free end? There's no load. 0. The change in shear is the area of the load diagram. What's the area of the load diagram? 0. 0 plus 0 is 0.
So wait, why is there not a shear at the...
Well, some forces in the y direction. What would your shear value be?
Okay.
0. There's no force. It's a very odd situation. And then the slope of your shear diagram is equal to the load, and the load is 0. So you connect those two with a flat line, you basically get there's no shear in this beam. So let's do the moment diagram. So starting at the left side, what's our bending moment? Is that a positive or negative bending moment? Positive. So we'll start off at positive m naught. Looking at the right-hand side, what kind of bending moment is that? Positive or negative? Positive. And that's also m naught. So the change in moment between 2 points is the area of the shear diagram. What's the area of the shear diagram? 0. So m naught plus 0 gives you m naught. And then the slope of the moment diagram is given by the shear, and the shear everywhere is 0. So here's a line with 0 slope. So in this particular beam, it looks like it has constant bending moment. So what's the maximum moment of the beam? M naught. Where does it occur? Everywhere. So in this beam, I have to make sure that my cross-section, my beam properties, were able to withstand a moment of m naught everywhere. This beam, however, what kind of beam do I need right at the end to withstand moment? Hardly any beam at all. But I need a lot of beam where the moment is maximum. So a lot of times, the shape of the beam can look somewhat like the shape of the moment diagram. So if you see a tapered beam that has this kind of shape, it's telling you that there's a big moment where the beam is thick, has a lot of capacity for bending, and very little moment where it gets thin. So if you see those kinds of shapes, you can see where the moment capacity is and where it's not needed, where it tapers off. Okay. Any questions about those? That only took 9 minutes.